There we go. That's good. Anybody look at last week's recording, see if it's any good? Didn't look at it? Okay. Oh, do we need to go over that?
Well, I like sort of kind of figured it all out now. Having those two online classes, but at first I know so long. Because at my other college, we didn't use anything like that. Nothing was online at all. That's like our grades.
They try to standardize it here, but in my opinion, it just makes it a mess. When I at New River, we build our own individual, and that has its pluses and minuses. Student has to learn something different for each professor, but I keep mine just as simple as humanly possible. I didn't already go over this today. Maybe not. That was this morning. Okay. This won't take long. There's, okay. So everybody knows how to get to Blackboard online classes. And then you have to log in. And your class is 2013, spring 2020. Okay. You notice all this crap on the left-hand side. The only two things you have to be concerned with are Start Here and Learning Modules. And you can get to Learning Modules from Start Here. Just go down. And there's a syllabus and the course instructions. There's your free Microsoft Office. All you need is a valid address. It has to be an EDU address from the college. And then here's the link to the next steps. Those are your learning modules. That's everything you need from now on. There's exam 1. And it's got everything you need. There's the PowerPoints reproduced, review documents reproduced. Well, this is the way the instructor sees it. Let me cut the garbage out. Now, there you go. That's the way the students see it. Learning modules. Now you have exam 1. PowerPoints are all here. Chapter 1 and 2, and they come in 3 different flavors. PowerPoint's here, PDF conversion, and the HTML5, which can be played on any browser, anywhere. Even on, say, you've only got access to a tablet. I don't know if they'll run on a phone, but you can try it. Those are your PowerPoints. Then your breadcrumbs here will take you back. Here's the first lecture right there. As you click on it, it goes to YouTube, pulls it up. I don't know if it starts automatically or not. I guess it does.
We'll come in on that day for review, and we'll.
Okay. So that looks a little blurry then. It could be because the built-in camera is not highest quality. So you can reuse stuff there. Kind of dark too. Okay. And those are your review documents. You have the review. You have a key to the review, which I didn't make for you. I think I passed out work problems. So yeah. Okay, so it's all there. A preview. Now we get down to review. Any more of that. Okay. So I always ask on a review day, if you have any specific problems we need to tackle first. Like if you went through and tried to work some of them and then looked at the work problems and still didn't make any sense, those are the ones we need to knock out. Okay. Got any?
I have a question on a few of them.
Okay. Did I start recording already? Oh, stop. Yes. Okay.
First one is number 14 on page 4.
14. Okay.
The answer he gave us didn't specify which actual answer it was. So I wanted to clarify.
Oh, okay. Oh, I see. I just sort of recorded a blurb here. 14. Okay. Let's see what we got. For the benefit of later viewers. So you're going to measure water into two containers, a 10 milliliter graduated cylinder with marks at every milliliter and a 1 milliliter with marks at every 0.1 milliliter. So you got two graduated cylinders. Let's see, let's make this one. Okay. And this one is the 10 milliliter, and this is the 1 milliliter. So that means 10 milliliters up here and 1 milliliter here. And this one is marked at milliliter intervals. Whatever that happens to be, 9, 8. It's not going to be scale. And this one is marked at 1 milliliter, so this would be 0.9, 0.8, 0.7 at 7 milliliter intervals. Okay. If you have some water in each of the containers and add them together, what decimal place would you report the total volume of water? Okay. Well, if we just pick something, you say we got this much water in that one, so I think 8, 7, 6, 6, 7. So that looks like 6.5 because the last one is uncertain, we estimated. And if we do this one, let's say 0.65 milliliters. Trying to draw some sort of comparison there. To what decimal place would you report the total volume of water? Well, if you add them together, we use our significant figure add rule, right? So we just add them first, like that, and then we say we can only report to that position. So to what decimal place? To the 0.1 decimal place. Oh, the answer's wrong. Okay, this is one of those cases. The key says C, which is 1 milliliter. And that just says we're only as accurate as these milliliters here. But actually it should be, and I need to make that correction. If this shows up on the exam and you put 0.1 milliliter and I count it wrong, then call me on it. It's supposed to be B. Based on this logic. Right? Did everybody follow me? Okay. So we're accurate to the tenths of a milliliter. only because we've estimated to the tenths here. We estimated to the hundredths here, but you're only as accurate as your least accurate device. Okay, another one? Sure, that's fine. Keep us rolling.
Number 42.
40.
on page 9.
No, there it is, okay.
I've done the problem right, like I said, that's the way you got on the page.
Uh-huh.
Like I'm not just like.
Oh, let me work it without looking at the explanation and see if I come up with the same answer. 'Cause that's the only way to check to see if I made a mistake on that. So 42 is convert 0.0494 cubic feet to liters. We want to find out how many liters that represents. Okay. And your conversion factors are given there as 2.54 centimeters is 1 inch, 1 liter equals 1 cubic decimeter. All right. So we're going from the English or imperial system to the metric system. So we're definitely going to need 2.54 centimeters is 1 inch. That's a conversion between those two. But cubic feet, I think we need to convert first to the metric system, because cubic feet we can relate that to inches, without being given, what the relationship there is. And then inches to centimeters. Then we can go to liters. Okay, so let's do it like this. We're going to chain conversion. Cubic feet. Okay. So now we're going to convert that to inches. Feet to inches. So we got 12 inches per foot. But foot's cubed, right? So we have to cube our conversion factor. Okay. That takes care of cubic feet, inches. Now we need to convert inches, centimeters. So that's 2.54 centimeters, 1 inch. And this inch is cubed now, so we have to cube that one too. Okay? We actually don't need the second conversion factor, and I'll show you why. This is cubic centimeters, right? I'm going to stick this one in here just for illustration purposes. One cubic centimeter is a milliliter. They're equivalent. Right? So now we got milliliters, and we want to go to liters. So 1,000 milliliters is 1 liter. Okay. Good so far? Okay. Now we just need to do the calculation and see if it comes up with that answer. All right. So start off with 0.0494. 12 cubed times that. So I'm going to keep it simple. So I just multiplied 12 times 12 times 12 there instead of trying to do the cube. And then 2.54 cubed, which would be 2.54. Okay. And then 1 and then 1. Okay. The rest of it has to be divided. 1 divided by 1 cubed is 1, 1, 1. And then the third is 1,000. So I get 1.39885 liters. And then we need to look at how many significant figures we can keep. Remember, conversion factors are exact numbers. We don't even have to look at them. We just look at this one. 3 significant figures. 1, 2, 3. Round it to there. this is greater than 5, so that has to be up to 10 carried 1.40 liters. Yeah, is that anywhere near? B, yep.
I'm not doing wrong.
Huh?
I'm not doing wrong.
Oh, okay.
I keep each individual one instead of keeping the outside parentheses.
Say that again.
Instead of keeping outside the parentheses, I keep each one individually. Like inches, feet, and I rather keep on the inches and on the feet. And meters and inches.
Oh, you didn't write cubed here? Ah, that'll do it. Yeah. Everything inside has to be cubed. Yeah. Both numbers and units. Yep. What is 12 cubed? 12 enter 3. Where is it? Here it is. 1,728 is 12 cubed. Did I lose anybody? Get that up there. So the last step is, how many of those are you allowed to keep? Hey, be sure and sign in. Okay, another one. Oh, keep me hopping. You guys good with it? You feel comfortable?
That's all I have.
Say something. I don't want to just randomly pick anything in here. Right? If it's not going to do you any good. Don't pick something that's giving you trouble. Good with all your definitions? You know the difference between a homogeneous and heterogeneous solution? Or mixture.
So we go over like mixtures and solutions.
Say again?
We got over the mixtures and solutions.
Mixtures, okay. Okay. Let me get my bearings here. I don't want to add anything to the discussion that's not needed. Yeah, no, that's not it. It must have been the first. It wasn't the first chapter, was it? Okay. Temperature. There we go. Oh, we talked about phases first. Solid, liquid, gas. I'll tell the difference. Which one holds its own shape and volume? Solids. Liquids hold their own volume, but not their own shape. And gases don't hold either. Okay, mixtures. So first of all, what defines a mixture? You have two or more substances together. But they can be separated. I guess the word is separable by physical means. Okay. Such as boiling, filtration, even chromatography will separate mixtures. So if chemical means are required, then it's not a mixture. you're actually breaking bonds to do that. So physical processes will separate mixtures. Then the next difference is, are they heterogeneous in nature? That is, the substances that are mixed together, are they evenly distributed throughout? So could I take a subsample from several different places in a mixture and get the same composition? In this case, no. There will be different compositions to be heterogeneous. Homogeneous, however, you can sample from anywhere in the bulk, and the composition, the relative percent of each one will be exactly the same. And we have a special name for this one. Solutions. Those are homogeneous mixtures. Now, I personally think there is some middle ground. It's not just a stark division. So some heterogeneous ones, you can get really close to homogeneous, but not quite there. And for these, I think a good example of that is, we didn't talk about this in class, colloids. Colloids are mixtures, and did we talk about solvents and solutes? We haven't defined those yet. Okay, so the components that are mixed together stay suspended indefinitely. But in a colloid, they're suspended because of the particle size, very, very, very small. So has anybody heard about Brownian motion? You had any biology courses that talk about Brownian motion in biology courses? If you look at really small particles like, good example, smoke. You have smoke particles in water. You mix it up and then let it settle. Look at it under a microscope, you see those little smoke particles, because they're so small, they'll be jiggling like this, jiggle, 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 jiggle. That's because the water molecules are banging up against them and making them jiggle. But they're not homogeneous in the solution. Colloids, the particle size is so small that they stay suspended indefinitely, but they're not solutions. Good example, Jello. Jello is a colloid. It's not a solution. Yeah. Actually, some parts of Jello are solution. Some parts are heterogeneous mixtures. So let's not flog that horse today. Let's just know the difference between the two. We used to define solutions in terms of whether they would separate under a gravitational field, but that's not valid. It's the composition. These have variable composition. These have homogeneous composition. That's the difference between those two. Let's see, did I say any more about that? We talked about difference between a chemical and physical change. I like to keep things real simple. In a physical change, there are no bonds broken in molecules. So if you have water molecule, any change that does not attack the bonds of the oxygens and the hydrogens is a physical change. Whereas a chemical change involves the breaking and formation of bonds. So for water, that'd be something like electrolysis, where you break the bonds and you produce hydrogen gas, oxygen gas. Let's see.
everybody good with memorizing your elements? And you're filling out those extra credits so you can rack up some points early on? Okay. Those are not due till the exam. So you got time. Yeah, you got plenty of time. And I know at the end of last week, I just introduced you to naming compounds. Right? So that's going to take some getting used to also. Practice that. Like most of my students, the real trouble comes from two places. What to do with polyatomics when they're combined with, say, trying to balance the charge. Right, if that's -1 and this is 2 plus, then you have to treat them as a unit, the parentheses. That gives them trouble, that gives students trouble. So they want to go in and say, all right, 2 and 6. That's not valid. Because polyatomic ions may behave as a single unit. And the other thing, let's see, what's my train of thought? Oh, acids, naming acids. That gives students trouble. And partly because there's really no logic to it. You just have to learn the rules. Because naming acids is a holdover, it's archaic. It was so embedded in chemistry by the time we got to modern times, we just had to make the best of it. So you have things like the rules where you name an acid. It depends, first of all, you got to have an acid first, a hydrogen plus something. And then you got to say, is there an oxygen in there? If there's no oxygen, you start with hydrogen. If there's any oxygen in there, you don't say hydro. You just look to this part and make the appropriate conversion, and then follow either one of them by acid. Okay. So that gets students trouble. That used to give me trouble too. Practice makes perfect. Do it enough times. And there's some really, really archaic names. In fact, they still use them in commerce. If you go to a hardware store or Lowe's or a place like that, say you want to refinish your concrete floor, right? You want to make it porous, right? So the finish will seep in and set. So what do? Well, you need to clean it, soap and water, and then you go in and you etch it with muriatic acid. They still sell it as muriatic acid. All it is concentrated hydrochloric acid. The muriate part comes from compounds of chlorine. Right, it's an archaic form. I'm not going to ask you that. It just illustrates it. Some things you just can't get rid of.
I have a question when you brought that on the board.
Yeah.
There. So unless it's specified as aqueous, then it's probably, for the
Yes.
purpose of the test, it's hydrogen chloride. So
Right.
it's specified
It's like that, and it would be a gas. And that would be hydrogen chloride, right? Dissolved in water, then it's the acid name.
and that's for all acids.
Most of them are gases, right? If you have the potential for liquid, I can think of one exception. One of your polyatomic ions is acetate. Okay, with a minus charge. Make an acid out of it. It's acetic acid. Vinegar. Diluted acetic acid, 5% is acetic acid or vinegar. But you can get acetic acid at 100% concentration. It's all acetic acid, no water. It's called glacial acetic acid. So in that case, there's no water, but we still call it acid. Right? And rather than hydrogen acetate. Okay. So that rule generally holds for gases like HF would be hydrogen fluoride.
But for the purposes of the test, don't treat it like it's an acid unless it's specified that it's
Aqueous, yeah. Or if it's like a word problem and it says hydrochloric acid,
Okay.
then you know that it's dissolved in water. If we do a reaction, say we have hydrogen chloride gas reacting with something else, some other gas in the container, then yeah, it's that convention swap. I wish it was all definite rules. But modern chemistry came in too late to correct some of those ancient ideas. Okay. Let's see. Yeah. Are you comfortable with naming conventions? Type 1, type 2, type 3. Want to review that? Okay. Type 1, type 2, and type 3 compounds. And these conventions are used for binaries, binary compounds. You have cation, anion, or in this case, pseudo-cation anion, because these are all covalent bonds. Okay, so first division is the first element of metal. So metal, non-metal. It'd be one of these two. So it could be metal, non, metal, non. And these are both, these are non-metals. Okay. So that means this one comes from the left-hand side of the periodic table. This one comes from that small area of the right-hand side. So if it's a non-metal, you go straight to 3. If it's metal, non-metal, then you have to decide between these two. On the decision tree, what you look for is fixed charge for this one. Fixed charge metal. This one is variable charge metal. Okay. Most of these will come either from the transition metals or creeping over in toward that dividing line between metals and nonmetals. So some of those are multiple charge. And I think, let me see, the review document, I want to look at which periodic table I gave you. Yeah, that one does have the charges listed in the upper right-hand corner of each one of the boxes. So you can check to see if it's. But as a general rule, I would say for this one, you go group 1, 2, and well, with the new convention, group 13, which used to be 3A. Those are all +1, +2, +3 charge. That's all they can have. These are the alkaline metals. These are the alkaline earths. And these are the boron, aluminum, gallium, and indium. They're all +3. Yeah, all +3. When you get down to tellurium, it has a possibility of multiple charge. But those are the metals that you use for this one. There are, I don't know if I mentioned it last time, there are a couple of examples in the transition metals where you only have one possible charge. One is silver at +1, the other is zinc at +2. So you're free to use either this one or that one for those. Since it's a transition metal, you could designate the charge if you want, or you could just say, use that convention, either one. And since I told you that, if you use one or the other and I count it wrong, call me on it and I'll make the correction. Okay, so the difference in metal charge differentiates between type 1 and type 2. So the variable charge, we need a naming convention to be unambiguous about the charge when we name it. So you name it with Roman numerals. That designates the variable charge. So we had something like a 3+ charge on our iron. We would start it off with iron 3, and then whatever the anion was. Let's see, just think of an example. Iron 3 chloride. Okay? So how would we write that in a formula? Well, you need the symbol first. Symbol. Okay? Then you need to know charges, right? All the halogens are what? -1. And our iron is 3+. Right? Because it tells you 3+, right? It has to tell you because it could be +2, +3. So then you balance the charge to write the correct formula. If you got 3 pluses over here, you need 3 minuses over here because compounds are neutral. So we need 3 of these. So it'd be FeCl3 would be the correct formula for that name. Okay. Then before we get to this one, then you have issues with polyatomics. The polyatomics could occur either place because all but one of the polyatomics is negative. Ammonium is the only positive one we're interested in. Right? So if ammonium were the cation, where would it fit? Right there, because it's only one charge. Polyatomics can only have one charge. They're fixed. Right? And since this is the only positive one, then as the metal substitute, it's only got one charge, so it fits there. But the anions can fit either place. And they are all fixed charges as well. You look at that list of polyatomics, you'll see that their charges are fixed and their names are fixed. Right? So you don't have to change chlorine to IDE, anything like that with a polyatomic. The name of the polyatomic just fits in the name of the compound. For instance, let's see if we can think of a weird one. We haven't talked about cyanide. So the cyanide polyatomic is just this, that, and one negative charge. So we could make, let's see, what's the favorite suicide pill? Potassium cyanide. Okay. So potassium is K for calcium, and then your cyanide. Then we check the charges. That's 1+, that's 1-. That's it. We're done. One more. Or if you mix cyanide with let's see, ammonium would just be substituted for that, so that would be a good choice. Let's say how about no, getting ahead of myself. How about gold? Let's see, what is it, 2 or 3? No, 1 or 3. Let's say gold 3 cyanide. So you need your symbol for gold, aurum. It has 3+ charge, and cyanide -1. So we need 3 cyanides, right, to balance the charge. So we have to say that's a polyatomic, so it's got to be like that and like that. Okay. In fact, I think one method of purifying gold from ore is to mix it with a cyanide, a source of cyanide, forms this compound and extracts it from the ore. And then you separate the cyanide from the gold on the other end, and you got your metal. Okay. So that's type 1, type 2. You know how if you're given a name, you ask, where do they come from? What part of the periodic table? Metal, non-metal, stick with these two. Non-metal, non-metal, go to this one. And then you have to subdivide that. Now the position, metal, non-metal, is easy for these two. Metal comes first, non-metal comes second, and you may have to change the name to IDE. Right, on the non-metal. But for the type 3 compounds, non-metal, non-metal, sometimes it's difficult to tell which one fits in the cation position and which one fits in the anion position, because they're not ions, right? They're covalent compounds. So some of that is just from experience, but generally speaking, the cation position is occupied by the element that is to the left or above the other one, most of the time. There are exceptions. So that's a good place to start. It'll give you, it'll knock out 85 or 90% of the possibilities. So non-metal, non-metal. So we can have, I don't know. Let's say, this one, phosphorus, tribromide. All you have to do with this type of compound is just write what it tells you to. 1 phosphorus and 3 bromines. Done. Or let's go the other direction. How about okay, if I pick that one, then found an exception already. This one. So in that case, the oxygen comes above sulfur, but it's second. Go figure. So this one is just sulfur trioxide. How about Okay, how about this one? What do we call that one? We never say mono to begin with. The first one, you just write the one. What's the prefix for 4? Tetrachloride. Okay. That used to be dry cleaning agent. Until Ocean, the EPA came along and said, too many people getting sick off this stuff. Dry cleaning workers were becoming desperately ill using this as a dry cleaning agent. It works great, but it's very hazardous. So I said, get rid of it, you gotta pick something else that's less hazardous. So they came up with something, but as usual, it's more expensive. Let's see, I was trying to think of something else. How about you can have combinations of halogens, right? You could have this one, I think. Okay, so this would be what? Iodine, penta, bromide. Okay, so you need to know your prefixes, what they mean. Okay, I'm kind of burned out. Let me look in here and see if there's one I missed. That's good. We won't get into organics. Save that for a whole nother course. But this is convention for, this is the beginning convention for naming compounds. We start off with binary ionics and then branch out from there. And then when you get into specialties, like into the organic chemistry, the overriding principle is still non-ambiguity. If I write a name in a document, you should be able to build the compound from that name, and it's only one possibility, vice versa. Well, let's see, what else can we do? Let's see, accuracy, precision, got that one down. That was pretty simple. Remember when you do a calculation and there are no parentheses in there to guide you, right? Your fallback position, order of operation, parentheses if you got them, then exponents, then multiply, divide, then add, subtract. So some of those questions in there are calculations, and there are no parentheses, so you have to use the proper order. And if you have a, let's do this one. And how do you keep track of the significant figures too? So this is number 32. If you do this one, or 7, 8, times 1.67.164. I'm going to leave the units out. Now, this is divided by 2.0, and we subtract 0.169. Okay, so we're going to have to do the multiply divide first, right? And because the significant figure rules are different for each one, we've got to resolve the significant figures for this one first, then put it together with that one. So let's see, 3.478, 1.164 times 2. So this one comes out as 2.0242. And we've got 3 significant, 4, and 4, so we're limited to 3, right? So this is going to be 2.02. So now we take 2.02 and subtract 0.169. So you have to line up the decimal places and subtract. So that's 1, 5, and 1 minus 8. I think that's right. And then we say, how far can we go over here? Well, we have to limit it to that position. So the answer should be 1.85, whatever the units are. Yeah, C's the answer for that one. That sometimes messes students up too. You start mixing up the calculations. Now, if they're all multiply divide, which unit conversions will be that way. So if you do a string of conversions, all the conversion factors are exact numbers, so you can ignore them and just go back to the original. After you do your calculation, your calculator spits out a number like this, and then you look back at your original and say how many significant figures come over here and round it off that many. If you do it that way, then you avoid rounding errors. If I were to round from this step and round that step and round this, eventually I could either be way up here or way down here, away from the answer. Let's see. I saw something in here that I wanted to hit on. Yeah, interpreting this figure. On page 15, did that give anybody trouble? Or was it self-explanatory? Page 15, well, there's several, 70 through 73. Yeah, 70 through 73 refer to that figure. So for 70, which of these figures best represents a homogeneous mixture of an element and a compound? So let's work backwards. Elements and compounds. So elements are going to be what? They're going to be either single dots of one color, or they could be double dots with the same color and shape, like for our diatomics. Do we have any there that are just elements? Okay, E's got the squares, that's just elements. But the other one is an open circle and a shaded circle, so that's a compound. And then D looks like it has a mixture of elements only. Some open circles, some shaded circles. So if we're looking for a mixture of an element and a compound, we can throw D out because it's only elements. And C we can throw out because it's only compound, right? And B we can throw out because it's not a mixture. And A is elements only, right? So it looks like E is the only possible answer for 70. And that means it's homogeneous. Element and compound. Okay, 71. 71 is looking for which represents a gaseous compound. So what are you looking for? You're looking for lots of space between the particles. And only two fit that, A and C. Then we look to see which one's compound. A is not a compound, that's the elements. So C could be, that's the only possibility. So that's a gaseous compound. 72. Right? Which best represents a solid element? Okay, a solid element is, and it says best represents. Right? So you want something where you've got just elements, right? So B and D could both be solids, but D has a mixture of elements. It's got open circles and closed and shaded circles. So B is the only element that satisfies, right? So this is a solid element. '73. Which best represents a heterogeneous mixture of two elements? Okay, so we need to throw out the anything that's got compounds in it. So we throw out E, we throw out C. So it's either A, B, or D. And then we look for mixture, right? B is not a mixture. It's got the only one shaded circle in it. So it's either A or D. And then we look for which best represents a heterogeneous mixture. Hetero means that they're not evenly distributed, right? And if you remember anything about mixtures, gases are always homogeneous, every single time. So A has to be thrown out. It's a gas, so it's going to be homogeneous. And that, by process of elimination, leaves D as the heterogeneous mixture of elements. Okay? So that was the whole purpose of that little thing. Just see if you could interpret pictures. How about separation techniques? Number 80. Sometimes it's hard to know what physical properties are being capitalized on in a separation technique. So, which of these separation techniques in D is based on differences in volatility of the substances? Does filtration have anything to do with volatility? No, that's particle size only. How about distillation? Does the volatility matter there? So, if you got a beaker of water and a beaker of booze, or crystal clear, 100% ethanol over here, which one are you going to smell? Just standing right here. I'm going to smell the alcohol, the ethanol. Right? It's more volatile at room temperature. So if we change the temperature, we can take advantage of the volatility. We can continue to raise the temperature of if they're a mixture, raise the temperature, and the more volatile substance will start to vaporize. Right? So the ethanol will come out first, and we'll collect it. We'll enclose it, so as it vaporizes, it comes up, and we can cool it down, back down, condense it. That's distillation. So the difference in volatility is the basis for distillation. Now, water and ethanol have a really, that's the distillation. You don't need to know this for the test, but water and ethanol are together in a distillation situation, illustrate a fly in the ointment, as it were, a distillation. You cannot distill ethanol from mash, say, and make 100% ethanol. It's impossible. The best you can do is 95%. What's the alcohol by volume, ABV. Okay, that's the best you can do. The reason is the ethanol, and I abbreviate ethanol like that. That's the ethyl part, and this is the alcohol part. Ethanol and water form what's called an azeotrope. And they will come off, they will distill off together. Only most of it will be this because it's more volatile. But some of this keeps tagging along. Water is volatile at any temperature. Liquid water is, right? It's just less volatile than this. So some of it always comes off with ethanol. And it comes off at that ratio. So it's mostly ethanol, but there's a little bit of water. So there's no way to distill and get 100% ethanol. So there are a couple of ways you can, right, because they sell crystal clear, right, 100%, 200 proof ethanol. So there's got to be a way. Well, one way is to distill, but distill and add a little bit of benzene. Benzene, water, and ethanol form a different azeotrope, right? And what it does is this holds on to the water in the liquid phase so that you can get ethanol out of it. And at a certain point, then the concentration of water increases to the point where not even that can matter. And then you get an azeotrope of all three of them coming off. But before they do, you can get your 100% ethanol out of it. You just have to sacrifice a little bit and leave it behind. The other way is to filter your 95% ethanol through some crystalline solid that attracts water. I used to do that in the lab. It's good for small scale, not for mass production. So I would have a bed sodium sulfate. And this would be solid, be perfectly dry. The sodium sulfate has an affinity for water, right? Water of hydration. So if you pour your ethanol, the water mix through here, it absorbs water and lets the ethanol come through, and you get 100% that way. I guess if you're going to make yourself a cocktail, and you want to start off with pure ethanol, you can do that because you can make enough. But if you're going to, if you're a moonshiner, then that's no good. Of course, moonshiners don't make 100% ethanol. There's no value in that. They usually water it down to what, maybe 70% or 60%, 120 proof, maybe even less, 90 proof. I think something like whiskey is like 90 proof, isn't it? Or 85 proof, something like that. It's like 40%. It'll still burn. I forget what's the concentration at which alcoholic whiskey or that type of will burn. 35% maybe? Yeah. It's lower than you would think. You can set it on fire, even with all that water in it. Okay, that's not important. Let's take that one, the answer to the question is B. And let's look at those other methods and see what is the theory behind those separation procedures. Filtration, of course, is particle size. Distillation is volatility. How about solvent extraction? What is solvent extraction? Solvent extraction in paper, well, no, solvent extraction is different. Actually, don't worry about it. It takes too long to explain. Let's go to chromatography. Right? What's chromatography's physics of separation? In a word, it's affinity. What's the affinity for the compounds or elements in the mixture for some material? Right? And you've always got a stationary opposed with a mobile phase. Right? So if you've got a bell jar with a lid on it, and you got some liquid down here, this is your mobile phase. And your stationary phase could be paper, it could be a glass plate covered with silicon dioxide or something like that, whatever that is. That's your stationary phase. So let's just use paper for simplicity. So you dip the end of the paper there, and you have like a wire suspending it. So this is your mobile phase, this is your stationary phase. Right. So you put your mixture up here. You don't want it in here because if you put it in the mobile phase, it'll just dissolve and spread out. You want it to have access to the stationary phase and the mobile phase at the same time. So if you've got, say, just two substances mixed together, one of them has a higher affinity for the stationary phase. Where will it be relative to the one that has the low affinity for the stationary phase? The low affinity for the stationary is going to move like crazy. Mobile phase is going to pick it up, right? And the one that has more affinity for the stationary phase spends less time in the mobile phase as it's moving, right? So it's going to be down here. Okay. So that difference in affinity is the basis for chromatography. All chromatography. That is one field of analytical work that's just exploded. And the selection of stationary phases is almost infinite. You can either get them in coated on plates. They use thin layer chromatography, that's what that is, in Europe a lot, and automated. But in this country, we prefer column chromatography. So you have these stainless steel columns, and they're packed with very, very, very small particle size stationary phase. So there's really a lot of back pressure because it's not a lot of empty space. So that's the name high pressure liquid chromatography. You got to put it under like between 50 and 100 atmospheres, push the liquid through it. But it's got lots of active sites to grab onto your moving compounds, and you get better separation. The term they use is theoretical plates. So the more theoretical plates you have, the better separation. Then, you know anybody in the down from Charleston in the refining, petroleum refining? No. organic chemists. Okay. Lots of times you'll see those towers out there from a distance. They've all got lights streaming up on them. Those towers, not all of them, but some of them, are distillation columns. Right? So they'll have something at the bottom that heat it up, and it'll vaporize. And as it moves up, there are plates positioned like this with drains off to the side. So they're kind of donut cup shape. So it moves up through the center, and it condenses and revaporizes. And the more plates you have, the better separation you get. And then they'll bleed off fractions as you go up. So the ones at the top are the more volatile ones. The ones at the bottom are the less volatile. So if you're taking crude oil and distilling it, you'll get the asphalts, the really heavy stuff at the bottom. And then as you move up, you might get the diesels, and then you get the octanes, the ones put in gasoline. And then you get the more volatile stuff, the cyclohexanes and the ethanes, even a little bit of ammonia. Benzene's in there somewhere. So that's distillation. That actually is fractional distillation. The one we described earlier with ethanol, that's simple distillation. Take organic chemistry. You can either set up a simple distillation, which works if the boiling points are very far apart, then simple distillation works fine. But if they're closer together, you need some way to add to plates. And we have distillation columns. Some of them are as simple as just when they make them hot glass, they just push dimples in from the sides. Gives them some place to condense on. Or you just take glass wool and pack it in there. And it creates these artificial plates. Okay. What else? How are we doing on time? 2:20? Okay, we got till officially 3 o'clock before we have to do lab. So how do you feel about this material? Oh, we got examples at the back, right? Oh yeah, we got to do those. Filling in tables. Did you have trouble filling in those tables? Here? No trouble? No, no trouble? We're good? Okay. Let's see. Symbols. Write names for the following compounds. Good for those? Okay. Did that extra credit help any? Good practice. Let's see. Chemical formulas for these compounds. Write the names for these compounds. Okay. Formulas. You know the difference between the law of definite proportions and the law of multiple proportions? That usually trips people up. Right. Question 86 and 87. What's the law of definite proportions? By the way, do you remember who devised definite proportions? I think it was Dalton, wasn't it? Definite proportions. No, Dalton was multiple proportions, wasn't it? Who's definite proportions? Okay, Dalton was atomic theory, and then did we even talk about it? I'm sure we did. I'm sorry? Yeah, there we go. Definite proportions, Proust. Okay. Lavoisier was conservation of mass. And then, yeah, Dalton was multiple proportions. Okay. So the law of definite proportions, number 86, would be the percent of lead by mass in the compound galena is the same for all pure samples obtained from any source. Doesn't matter where it came from. If we identify it as a compound, the percent composition is always the same. That's definite proportions. Whereas multiple proportions requires a series of compounds where you hold binary compounds where you hold one of them constant. It's like that's your unitary, and then the rest of them vary by whole number multiples. Now, I think I showed you the nitrogen oxygen compounds was an example. So that was B, the mass of oxygen that is combined with a fixed mass of nitrogen in each of the binary nitrogen oxides can be expressed as a ratio of small whole numbers. Okay, let's see. Okay. If there are no problems, we'll just you want to take a short break, then we'll come back and finish the lab. Let's just do it in here since we don't need lab space. Graphing, wasn't it? Yeah.
Intro to graphics technique.
Yeah. Did you get a chance to look at it? No. Okay.
I'll do that.
We'll see. My 203 class gave fits. Well, there were a couple that eventually caught on, but it was a problem for most. I don't know what it is. Maybe just the concept of graphing just eluded them.
I have a question on these.
Mm-hmm.
I mean,
Okay, which one?
number 48, page 10.
Okay, page 10. Okay, chapter 1. 48. Okay. Mike?
Question about that.
Yeah.
Where, 100 gram body count.
Manganese makes up 1.3 times 10 to the minus 4th% by mass of the elements found in a normal, healthy body.
So it's per 100 grams of body.
Yes. How many grams of manganese would be found in the body of a person weighing 206 pounds? So that requires that you, I think the best approach there is convert pounds to grams. And then you can say 1.3 times 10 to the minus 4th grams manganese per 100 grams of body. And because the question is how many grams of manganese? And then if you know the total number of grams in the human body, then it's just a matter of multiplying that times the percent value. See what I mean? Yeah. Yeah. It cancels the denominator and leaves you with just a whole number of grams for the whole body.
Do you have an extra printout of the tracking techniques?
Another printout?
Yes.
Yeah, I think so. I think so. Somewhere. And I got some extra graph paper too. Here we go. Well, let me see. Does it look like this?
Oh, yeah.
Does it have a bonus section in it?
Mhm.
Okay.
Thank you.
Anybody else? Need any extra paper? You haven't tried yet, right?
No, I did try, but I'm pretty sure I did it all wrong, so I just need
Need some
a
more?
whole new one.
Let's see how many more pages I got. Got 5 more pages. Anybody need extra? No, not yet. Okay, I'll hold them until you call for them. Okay. I'll just let it keep recording. And now we're gonna be talking about the lab. graphing techniques.
Actually, I'm familiar with that.
Okay, let me pause this. Here we go. What do we mean by a graph? What do you think we mean by a graph? Well, one definition is a visual representation of data. That's really not complete. The visual representation of data relationships. Because sometimes you can represent results of an experiment as a picture, right? That's really not a graph. So we're going to focus here in graphing on the Cartesian system. Remember that? Has anybody had graphing in math class? Okay, good. Oh, good. That makes things so much easier. So the Cartesian system has what? It has two axes, and it's on a two-dimensional plane, right? So you've got an abscissa down here, the x-axis, and you got an ordinate here, the y-axis. And any point in this field can be expressed as a pair of numbers. The first number in the pair refers to where on this line it occurs, and the second one on this line. So what that means is, if we've got one with a number represented by that and a number represented by that, then its position is where those parallels cross, right? And then we have a value of x1 and y1 for that. Okay. Now, in science, we usually restrict the use of the abscissa and the ordinate to variables. You know, what do we mean by the variables? And in any experiment, the scientist usually controls one variable and then measures another variable response to the change that he or she made in this variable. So that means this is the independent variable, which means you can make it whatever you want to. And then this is the dependent. And it depends upon whatever you do to this one, right? So in this data point, this is the one I changed, and this is the response to it. Okay? And you can do that to any of them. You can change this one all you want, and you might get another number up here. You might get a number down here, whatever. Depends on the experiment. Okay. Let's see. All right, they talk about quadrants. So in math, that's valid, right? Because you're going to say that the ordinate goes like that, and the abscissa goes like that. So you have 4 quadrants. right? But most of the time in the sciences, we only use this quadrant. Sometimes we stretch this quadrant over, and occasionally we stretch this one a little bit. But most of your information is going to be in this quadrant. See, for them, it's the A quadrant. And this is the origin. So for our data point, this one is 0, 0. Okay? So that means the value for X is 0, the value for Y is 0 at that point. Okay. So, well, I'll leave that quadrant up there. If you say we plot our points and they come out like this, maybe not even that good, right? Because there's some experimental error involved. Say this one is up here and this one's down here. So what do we want? Well, it looks like it's approximating a straight line. Not exactly. So what we draw, we don't want to just connect the lines. And in graphing terms, that's called splining. Splining just connects that like that. Sometimes that's valid, but in this case, we want a trend line. What lines will minimize the error, that is, the variations, right? You want a line that's close to everybody. Well, the way I drew it, it turns out that if I draw a line through these two far points, right on these two and the same distance for those two, so that's a good trend line. Now, for our data set, we know what happens from here to here to here to here. So our trend line can give us reasonably good values if we want to use that line to say, what if? Right? What if I'm not, I have data down here, like I want to know what would Y be if I chose X here, right? So none of these fall exactly on it, but the line is there, so I can say, okay, go with here. That's my Y for that X. Use that trend line to say, what if? Now, what's done sometimes is, well, actually, since we don't actually have values in here on the line, the only values we have are like there, 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 then anything else on that line inside our data set is called an interpolation. I don't think they put that in here. But if we extend the line on either end outside the data set, that's extrapolation. Okay. And there are statistical ways to analyze data like this and say, okay, how good is that extrapolation? And normally what they do is they have, in conjunction with this line, they have another, say, maybe a dotted line or a light gray line that gives you confidence limits along the way. The confidence limits should be fairly close right in here. And then you really become less and less confident the farther away you get from your data set. Okay, so this would be a confidence interval. It could be here, it could be there, it could be anywhere in here. So those are our confidence limits. That's really CL. I don't think they talk about that here either. Okay, so what types of curves or graphs or whatever can we get from our data? Well, let's stick to that one quadrant. I don't want to get to, that's good enough. So say we have a data set here with X or Y as our independent or dependent variable. And say we do produce a straight line. Right? So if we're going from low to high this way, that's our origin. We're increasing this way, increasing that way. Then as X increases, what happens to Y? Y increases too, doesn't it? Right? So that's called a direct proportion. But what if as X increases, Y decreases? Right? Say the line goes this way. As X increases, Y decreases. That's an indirect, or no, inverse, excuse me, an inverse proportion or relationship. Okay? Notice in terms of, if they're both straight lines, in terms of straight line equations, this one will be, remember, y equals mx plus b, straight line. The m is the slope. So the slope on this one will be, m is positive. Right? Slope on this one, m is negative. Right? So whatever m happens to be, there'll be a sign buried in it. But all graphs are not necessarily straight lines. We prefer straight lines. They're much easier to deal with. And sometimes when we get non-straight line, we try to do transformations that straighten them out. Right? Here's one example. If we change the pressure of a gas and we hold the temperature constant, and we don't add any gas to it. So it's just the relationship of pressure and volume. If we change the pressure and we measure the volume as a consequence, as we increase the pressure, what happens to the volume? Volume goes down. And this relationship actually is a hyperbola. That at any point on that curve, the slope will be negative, right? And in terms of calculus, it's called an instantaneous rate or an instantaneous slope. So it's the tangent to the line at that point. Right? So the tangent of that line, that's negative slope. It's a different slope over here, but it's still negative. Right? So that's the trouble. Depends on where you look on the curve as to what the actual slope is. So we want to straighten it out. So we do a transformation. And the transformation we use is we take the volume values, we leave these alone, create a new data set. We keep the pressure, but whereas we have a pressure volume list here with various values, pairs, right? X, Y. We take this one and do the inverse and get new values here. Then we plot this one against this one. And if we were to do that, right, for the 1 over V and P, we get straight line. Okay. Now, why is that? Well, the funny thing about it is that the relationship in this hyperbola is typical of P times V equals a constant value. Okay. That's actually Boyle's law. But we want to do the transformation. That's not a straight line. We know it because we graphed it. But if you divide both sides by V, we get what? P equals K over V. Well, let's separate out the K and 1 over V. That's valid. Right? So now we have Y M X. And B is equal to 0. Okay? So by doing this transformation, we get that constant is our slope. And plot P against V. Okay? Now, one of the questions in there asks you to do that. Let's see, where am I? It's a little talky. Okay, now, the question becomes, okay, that's a lot of the stuff I just talked about. So's that. Examples there. You can get multiple curves, like this one. This is a titration curve of an acid and base. So there's no way to get a straight line out of that. You just have to deal with it. Or this one is, let's see, a temperature time graph of nitric acid and sodium hydroxide. This is what's known as a discontinuous plot. So you have this one plotted, and then you have to jump up here and plot the rest of it. But that's in the bonus section, I'm pretty sure. Okay, so page 25 has some definitions that you need to fill in. Those are fairly simple. Number 3. Let's answer number 3 with specific data. Now, why are we bothering with all this stuff? Would it be easier just to go in the lab and do the experiments? Well, humans are visual creatures. You can detect trends. You can make predictions. You can gather insight about a data set, an experiment, better if you can represent it in a visual format. So that's why we graph our data, because some things just jump right out at you that you wouldn't see in just a list of numbers. So how are we going to graph this stuff? Well, let's see. Let's take number 8 data. Okay. We got this data set. It looks like this. Temperature, degrees C. Volume in liters. So we got minus 50, minus 10, 0 degrees, 25, 50, and 100 degrees C. And for each one of these temperatures, we measure the volume of the gas as it changes with temperature. So at this temperature, 50 degrees, minus 50 degrees centigrade, the gas occupies that many liters. Then as we heat it up, it expands. Right? This is a direct proportion, or not direct, yeah, direct proportion. Two more. I got a loose thread in here. I'm messing with my. Let's see it now. Okay, so how do we plot this? Or how do we graph it? Right? Well, first of all, you identify your units of measure and which is independent, which is dependent. That depends on the experiment or how the word problem is given to you. So this says, here it is. Here we go. This says a study was made of the effect of temperature on the volume. So that implies that the temperature was changed by the experimenter and the volume was measured in response, which means the temperature is the independent variable. This is our X value, and this is our Y value in response to it. So that means when you look at your grid, we're going to have a y-axis, and we're going to have x-axis, which is our independent variable. So you label your axes, right? So this one, the x-axis is going to be temperature in degrees C, and this is going to be volume in liters. And then, of course, you want to name your graph. Right? So you look at the expression here. It says the effect of temperature on the volume of helium gas. That would be the label for this whole graph. Right? The effect of temperature on the volume of helium gas. You identify your, okay? Now, you may wonder why I drew this out here. Well, actually, how high up does the temperature go? The temperature goes up to 100. Let's extend this even further. And I'll explain why in just a minute. Okay. So this is going to be our 0, 0. That's the origin. And we're going to use this quadrant and that quadrant. Why? Because the temperature is below 0. Right? We need room out here for 0. So how do you deal with that on your graph? Well, there are two possibilities. If this is going to be the axis that needs more space, you probably ought to turn your graph into landscape and use the longer axis for this one. Okay. And use the shorter axis for this one because, right, it only goes to 458, 766. Right? So if you turn your page on the side, you've established that it's better as a landscape. Okay? That's one of the things. So if you go back to question 3, you need to know the units on your axes. You need to decide what's the orientation, and the largest axis should be, the longest axis should be on whatever's available. And if it needs to be the x-axis, then you turn it landscape. Okay. Then you need to look at maximum ranges. What can you fit in this thing? So if you take, say we take this one, turn it landscape, then you count, well, how many major squares do you have? Right, this has got major lines and minor lines. So let's see how many squares we got on this axis. First of all, what's our range? we're going from minus 50 to 100. Range is 150. Right? We need room for 150 at least. And I'll give you a heads up. One of the questions, 8(5) on page 27, asks, at what temperature would the helium sample have a volume of 4.2? Right? So 4.2 is less than that, so that means you're going to need more negatives out here to accommodate. Right? So we're going to give ourselves plenty of room out here. So maybe 50 would be here, and it'll give us some extra space. Right? So 150, we really want to go maybe to 170, 180, whatever's convenient. So this is the art right now of graphing, is deciding how to set your graph up on the available space. But let's see how many squares we have. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 23. So we've got 23 squares. And that's not going to go into it evenly. So let's say we're going to use 20 squares. So that would be, suppose we want to go, instead of 150, suppose we want to go 200. Then we would need 10 squares, right? Is that right? We use 20 of them. No, excuse me, 20 squares with 10 each. So if we use 20 squares, we're going to put 150 of them on this side and 50 of them on this side. No, that's not right, because we need to go below that. If we go up to 100 here, what if we just do 100 on both sides? Wouldn't that be easier? Yeah. Well, that's what I'm saying here, 200. So if we go up to 100 here and go to a minus 100 here, go up to positive 100 here, then we could fit that evenly in the middle of the page, roughly. So let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That one there, and then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, that works. So if you start at the left-hand side and go 10 over, that's where you would put the vertical line, right in the middle of the page. 10 squares over, you put your y-axis straight up and down, like draw it in a dark line or something. And then to the left, each square would be worth -10, all the way down to -100. And on the right of that one, you go up +10 to a +100. Okay? So that covers the x-axis and gives us plenty of room. So our data is only going to be good here, and anything else we do to it will be extrapolation up to 100. So we're actually going to graph from here up to here on this axis, and wherever the points lead relative to the vertical axis. Okay, so now we've got landscape. We need to see how much room do we have for 4 to 7. Well, if we make a whole number 8, then we can start at the bottom and say, how many do we have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 16. Okay. We can go 16 blocks vertical here. Why did I choose 16 blocks? Because if we make a whole number two blocks, notice how those main blocks are divided. Each one has 5 divisions. So if we go 2 blocks, you've got 1/10 of a division in there. See what I mean? So we've got a block here and a block here, but we're going to make this one 1. And each one of those little ones will make it now 10 divisions. So you can easily do a 0.1 for those and estimate the other one in between in the little tiny block. Okay? So we've got 1, and we're going to go up to 8. So 1, 2, 3, 4, 5, 6, 7. That's not a scale, really. But that's the first thing. Decide what's your scale. Well, after you've decided which axis is which, then how much of the axis do you need? Whether you need portrait or landscape, depending on which axis needs the most room. And actually, the temperature does need the most room. So now we've got it laid out with our ordinate is actually in the middle of the page. And our abscissa is at the bottom. So once you mark those off for degrees and volume in liters, then you can plot the data. We've divided what is the scale units. Okay, we did that. And how many of the units are included in each scale unit? So in this one, our scale units are 1, 2 through 8, and we divided that in 10. In this one, we went 10 by 10s for each block. So that means each one of those blocks is 2, because there are 5 of them. So 2 times 5 is 10. Okay. So each one of the little tiny blocks in this one is 2. And each major block is 10. Okay? So once you've established that, then you can go put your data in place. Now, I don't know exactly what it'll be. There'll be something over here with 50 at 4.58. It'll be right in here somewhere. And then there'll be 5 at -10, something like this. So it'll be a shallow curve like that. But this is temperature -50 and 4.58 at that point. But if the question is, for instance, what was that question? 5. Well, let's do 4 first. At what volume would the helium sample have a temperature of 5 degrees? So once you've got your trend line drawn with your data points, then you say at 5 degrees, go up to the line and say, okay, that's what it would be. The value of the volume, you can predict it. Then it says, at what temperature would the helium sample have a volume of 4.2 liters? 4.2 liters is well below, so we have to extrapolate until we get 4.2 out here, and then we drop down and say, that's how you visually do it. You can also do it once you know what the formula is. So if we do 6 and 7 first, then we can use that formula to calculate the answer to 5. Okay? Do I need to stop for a minute? Let you catch up. Now this is how you do that stuff by hand.
What number do we put at the bottom, like 5s or 10s?
10s.
10s?
Yeah, 10s. For each block.
10 for each block.
Right. Right. We only had 1 block at a time for these. This one we used 2 blocks because we had room for it. But this one, we have to use 10 degrees for each block. That means each one of the tiny increments is 2. Okay, let's see. So, what's the slope of a line? Definition. Rise over run, isn't it? Yeah. So the rise, so we have that point. Go further out, 100. Let's assume our line goes through this point and that point. So we can use those 2 data points directly. We don't have to read them off the graph. So what would the rise be? It would be a change in Y, wouldn't it? Or a change in volume. So this is the rise. Delta V, change in volume. And this is delta T, change in temperature, is the run. So this is change in Y divided by change in X, change in V divided by change in T. So what would that be? Change in V is the farthest to the right minus the farthest to the left of the V. Well, actually, highest minus lowest. So this would be volume 7.66 minus 4.58. Right? So that's the change in volume divided by the X, change in temperature. So that would be 100 minus a minus 50. Right? So that's actually, what is it? 3.08 divided by 150. That would be the slope of the line. And it's a positive number, right? And that fits with the data because this slopes from left low to right high. So it's a positive slope. But it's a very shallow slope because 3.08 divided by 150 is 2.05 times 10 to the minus 2. Or it could be 0.0205. Either one. So that's the slope. That's equal to M. Okay. What is the y-intercept? That question is y-intercept. Calculator. Y-intercept is 7. What's the y-intercept? Well, do we have a value for zero temperature? Yeah. Now, strictly speaking, that may not be exactly on the line, but we're keeping it simple, right? So the y-intercept is where the line crosses the y-axis at x equals 0. And here's y. Where is it? Now do this. Y equals mx plus b, y-intercept, right? So if x is 0, that term goes away and y equals b. So at x equals 0, right here, where is y? It's right there. That's the y-intercept. That's where the line crosses the y-axis. In this case, we're taking b as equal to 5.60. Okay? Do I need to do that again? And then the expression of the equation is y, well, actually, let's use the units, the variables that are actually given. So y is V, volume equals M 0.0205 times X, which is temperature, plus 5.60. So that's your equation for the line. Now, if you want to find out, let's see, what was the question? At what temperature would the helium sample have a volume of 4.2 liters? Volume of 4.2 liters. Right here. Now you just solve for temperature, right? I think I did this earlier, and I think temperature is like minus 68 degrees C. Something like that. You can check me and see if I'm right. But how would you solve the equation? Well, you take this one over here. So this would be 4.2 minus 5.60. You have a minus number over here. And then you hold this t and divide both sides by this one. So divide by that is 1. Divide 0.0205 here. And you get a negative 68, I think. If you estimate it from the graph, probably the best you could do is say, minus 70. The nice thing about this type of data nowadays is that there are a number of different programs that'll do all that for you in the computer. All you have to do is put your data in. It'll plot it. You can tell it to draw a trend line, see if it's straight. It'll give you the equation for the trend line. It'll also tell you how good the trend line is. It'll tell you what the deviation is, average deviation for the line. A whole bunch of statistics it can work out. But we need to walk before we can run. Do it by hand. Then if you do it in the computer, you'll understand what you're doing. What do they say? Garbage in, garbage out. If you don't know what you're doing, then you can put stuff in the computer and it'll spit out garbage because you put garbage in. So you got to know what you're doing first, right? Or what's another saying? Computers can make a chemist more productive, a good chemist more productive. But computers will not make a good chemist out of a bad chemist. Okay, that covers volume and temperature. The next page, we're going to plot, pressure against volume. So it says the temperature of 32.1 gram sample of methane was held constant at 298 K. That's important. Its volume was measured under various pressures. So that means that you change the pressure and you measure the volume. So that means the pressure is the independent variable, the volume is the dependent variable, which means volume is on the y-axis, pressure is on the x-axis. Now for this one, those are all positive values. So we could stay in this quadrant and be just fine. We just stick the origin in there. We just have to decide which orientation is best. Do we want a landscape or portrait? Okay. Any questions on this one before we leave it? And this is all being recorded. Okay. Let's see. Kind of scooting off the edge over there. There we go. I hope I'm writing big enough so it'll show up on the video. Okay. Because I know the camera that's built into laptops is not the highest quality. At least not the one that the government gave me. I think it's been hand-me-down 3 or 4 times before I got it. Okay. So for this data set, what do we have? We have pressure and volume. Okay, well, I mentioned that a little earlier. Pressure times volume is a constant, which is basically Boyle's law. And if you go down and you multiply pressure times volume for each of these, you'll find that they're pretty close to the same number. So they're constant. But you don't need that to do the exercise, that just proves the relationship. Well, let's see, maybe I don't have to draw it. Let's see what kind of data set we've got here. Pressure in atmospheres, volume in liters. So pressure is 0.5 atmospheres. We go up by increments of a half, it looks like. Okay. And at each one of those pressures, we measure a volume. 97.8 liters and 48.9, 32.6, 4.5. I bet this was a generated data set. They didn't actually measure these numbers. Okay. So basically, multiplying each one of these should give you 48.9 or 49 roughly, right? Because 1 times that is 48.9. So the rest of them should be that same number or close to it. Okay, so we got our data set. Now we need to decide, is it units of measure, right? And then we decide, is it portrait or landscape? Well, let's see which one has the broadest need. Looks like volume has the most need. So since volume is the dependent variable, pressure is the independent variable, we probably should put this one on the short side. So portrait would work best for this one. This one would go along here, and this one has the greater range. It would go like that. So that previous one was better as a landscape. This one would be better as a portrait. So let's see what's the scale. 0.5 to 3.5. Well, let's see, if we're going from 0 origin, we'll probably go up to 4 would be a good round number to head for. So let's see, how many squares do we have? 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. Okay, so we could go up to 17. That would include everything but the last square. And if we have 16, let's see, 16, and we're going up to 4, that means we have 4 squares each. Right? So if we count 0 as this corner, and we count over 4, that's 1 atmosphere. Count over 4 more, that's 2 atmospheres. 4 more, 3 atmospheres, 4 more, 4 atmospheres. Okay? So then if you go only 2 squares, go halfway in between 0 and 1, there's your half. Halfway between 1 and 2, there's your 1.5. Okay? So we have 4 big squares, and then we're going to have how many little squares between the majors? 20. 5 for each. 5 times 4 is 20. So that means 2 squares equals 0.1. It's not a problem though, because the third digit they're always 0. Right? So you're going to fall right on a line somewhere. Okay, we got the x-axis done. Now we need the y-axis. So the y-axis looks like we're going to go up to maybe 100 would be a good range to fit everything in. We go from 0 to 100 on the left. Let's see how many squares we got. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So if we, 20 squares represents 100, then we probably are talking about if you only went up 10, then each one of them would be 10. But we're going up to 20, so that means we're going to have 2 squares for each 10. Let's see if that works. Let me mark it. So if that's 10, 20, 30, 40, 50, 60, 70, 80, 90, yeah, 100. So 100's up here. Okay, so that if you do 2 squares for each 10, that means each one of the little ones is 1. Right? So 2 squares to the first step is 10. We're not even in the graph yet. But do 4 more little squares and you get to 14. Does that make sense? Okay. And the only way to know for sure is to mark it off with your pencil in equal steps and say, all right, does it fit? Okay, yeah, it fits. So now we've got our axis labeled with pressure on the x-axis in portrait, volume on the y-axis, and we've got our axis label. So we have pressure, parentheses, ATM, and on the y-axis we have V, parentheses, L for liters. Then we got to name it. Right? So we look at the description, and it says the volume of methane as pressure changes. Something like that. Okay? And then you got your portrait. You got your labels down here. Pressure, volume, title, mark off. And then you plot your points. And like I said before, this is an inverse relationship. Which means as pressure goes up, volume goes down. Only it doesn't do it linearly. It forms a hyperbola. So then the next step that's called for in here is do the transformation. Just go through and take each one of these values and do the inverse. So that's a comma. And do the inverse of these numbers, right? And they'll be small decimal numbers. And then you plot, do the same thing all over again. Just take another portrait and set up your pressure the same way you did the other one because it's already established at that scale. And then you set up this scale to cover the values that you've got from there to there. Okay? What would that be? Volume, 97.8. I'll start it up. I'll start the ball rolling. 97.8. And then there should be an inverse key on your thing, on your calculator. So I got 0.0102. 0.0102. And then 48.9. Invert that one. 0.0204. So they're probably going to go up by increments of 0.01. I bet this one's 0.03 something, this one's 0.04 something. We'll go on down to this one, 0.07, 4 decimal places, 1.4. So that gives you the full range. And this, probably you want to set a range here. Instead of V, you're going to have 1 over V, and you're probably going to go up to 0.08. Right? So you can subdivide it to get the maximum range out of 0.08 on that scale. That would cover all of these values. And you already got this one established there. Right? So then you plot it. And if you plot that, you should get a straight line. With a slope, you do the slope the same way as we did before. Right? Change in y over change in x. And then the intercept is going to be 0, 0. Y-intercept. It's going to go through the origin. Let's see. What am I leaving out? Oh, units. All right, this doesn't change. This is going to be atmospheres. What are the units for this one? When we took the inverse of these numbers, what else did we do? Took the inverse of the units. So 1 over V, like if we had this, 97.8 liters. So we took the inverse of this, but we also took the inverse of the liters. So how do we express liters as a unit of measure? Inverse of liters as a unit of measure. Liters to the -1. Right? Now, -1 means inverse. So that would be your unit of measure. Now, there's one question in here that might throw you. Let's see, where is it? Oh, parentheses 6 at the bottom of the page. It says, use the graph prepared to determine the pressure of the methane sample when its volume is 40 liters. So its volume is 40 liters. So it'll be in here somewhere. But a curve like that does you no good. Straight line works much better. So how do you get 40 liters out of this straight line graph? Well, you can't use that scale, right? Because it's 40 liters, not inverse liters. Liters to -1. So what do you do? Take the inverse of that value. So you invert the whole thing, right? Now, that is represented by, let's see, inverse of 1/4 is 0.25, so 1/4 would be 0.025. 0.025 inverse liters. Now you can look at 0.025 right in here somewhere. Go out there, drop down, and find your pressure. Okay? Let's see. What else? Oh, then we're into the bonus section. I don't know if you want to mess with that. Can if you want to. Yeah. Takes a little more effort. That's why I made it a bonus. And I actually did these data sets in the computer, right? So here's temperature volume, okay? I think I did that in Excel. And here's the straight pressure volume. that. And then here's the inverse, pressure inverse volume, straight line. Oh, and here's the titration curve. This one though, I couldn't draw a straight line, a smooth curve with my software, so I had to do a spline. So I just connected the dots. Kind of cheated. This one I did by hand. Well, I did it both ways. I did it by hand first, the disconnected, and then I put it in the computer. Actually, I had to put it in as two separate data sets and graph this one and then graph that one separate. That's the only way I could do it. So I'm not expecting you to do that fancy. If you want to attempt it, fine. It's worth a few points. Any questions? I think the rest of the information is you can probably dig out of the document. 3:30. Does that mean we're finishing early? Ooh, we're good till 5 o'clock officially. But if you're good with the lecture part, so you'll be ready for the exam, which will be next Friday, and the labs. Oh, let's see. Are we going to have another lab when we come in next week? Let's see. Let me check that, because I'll have to hand that out now so you'll be ready for it. No, we don't. Right? We have the exam. Oh, that's why I didn't put a lab on that, because we're going to cover 2 chapters after the exam. We're going to need all that lab time. And then the following, we'll do laboratory techniques. Now, I can give that one to you now if you want, so you can be putting your lab notebook together. Actually, there's no formal lab report on that one. It's up to you if you want it, or you can pick it up next week. If you're afraid you might lose it. Okay.
So when we take the exam, is it like the full time as like the lecture, or is it like time?
I used to time them, but that didn't work out too well. It would be better if you could finish it, say, in an hour and 20 minutes tops. Then that would leave us enough time to get through both of those chapters.
I just didn't know if it was like time, it was like 30 minutes.
No, no, I'm pretty flexible there. And with so few people in the class, I should be able to get it graded before you leave, so you'll know where you stand.
So do we turn this, the package we turn that in next week?
Actually, since we're not going in the lab next week, you could take 2 weeks to do it. Right? So if it were me, I'd get the required section done before next week, and then if I've got some extra time, I'd jump into the bonus and see if I could grab myself some more points. And if you get into it, actually, if you get into the bonus before next week, you can pick my brain on it.
And then the other bonus stuff is due next week, or just in 2 weeks?
At the time of the exam, those two, name a compound and periodic table, yeah. Okay, so I'll put this back in here. We're good to go. I wonder what it's doing outside. Is it getting colder?
It didn't feel too bad earlier. No.
They said we were supposed to get some snow on Saturday.
Really?
Yeah. I don't know. It's going to have to go away to get here. Oh, more practice exam copies? Let me see. I usually make extras. This over here. Let's see here. That's, yeah. About that later. There's some more graph paper. review. Yeah, I got one. Yeah, they're good to practice on.
Yeah.
You can get the government to pay for the copies, that's even better. You don't have to use all your ink. He's back in the lab. Let's see, did I shut that down?